Okay, we definitely have critical mass now. So, good evening. Thanks everyone for coming. Tonight's about mortality improvement, and I thought I would talk for about 6 minutes, and then we'd be ready to do the sample questions from the SOA exams. And then, if we still have time after that, I've got some exercises as well. But so, what mortality improvement is about is the idea that that Q sub 60, which we think of as a constant, the probability that 60 dies between age 60 and 61, we think of that as a constant over time. But the idea behind mortality improvement is that Q sub 60 declines over time. Or at least when we get to Lee-Carter model, has a tendency to decline over time. And the question is, by how much? So first, instead of saying Q sub 60, since it's going to decline over time, it's going to be a function of age and time now. Okay, so Q is going to be assumed to decline over time, and by how much, the answer is provided by this new function. And this chapter is all about this function, phi of x and t. And we can think of phi of x and t as the proportion by which Q decreases. So if phi is 0.5, that means mortality drops in half that year. So mortality drops in half. So that's the way to think of it. If phi is 0.1, mortality drops by 10%. Okay, so for example, if phi of 60 a year from now is 0.1, and if Q of 60 0 is, I don't know, what's a good Q sub 60? I'm just going to guess 2%, maybe 2% of 60-year-olds die. Then a year from now, Q of 61, a year from now we expect Q sub 60 to drop to Q sub 60 0 times 1 minus phi of 61. Okay, so we expect it to drop by 10%. That's going to be 0.02 times 0.1, which if you work that out is equal to 0.018. So it's a lower Q. Folks are more likely to live. I don't know why that 8's not coming through. Sometimes takes the screen you see a minute to catch up. There we go. All right, so that's the idea. And then in this chapter, there are 3 concepts. Okay, so 3 concepts. And one we just did. The first concept is phi of x and t. Occasionally we just think of phi of x. That says the improvement every year is the same. It just depends on age x. Okay. The second concept is cubic splines. And the idea behind cubic splines is often we know facts about the mortality improvement before year 0 and say after year, just to pick a number after year 15. And we know a lot about it there, but we don't know in between, we don't know what's going on in the years in between. And we may know some things about the derivative. Okay, so phi prime of phi 0 we might know, and we might know phi prime of x 15. And then what we're trying to do, we're trying to come up with a cubic function that matches the values of the function and the derivatives at these points. Okay, so a cubic, and that's really all you need to know. I mean, g of t is at cubed plus bt squared plus ct plus d, and we use it to match the values at these points up here. Okay, and you know, g prime of t, lucky for us, is very easy. This is back when we thought calculus was going to be easy, that to take the derivative of a polynomial is nice and easy. 3at squared plus 2bt plus c. So those 2 things, phi of x and t and cubic splines, are pretty easy. The last topic is kind of a pain. Okay, the last topic is the Lee-Carter model. And the Lee-Carter model is about modeling phi of x and t with respect to time, modeling mortality as a function of time. And unfortunately, instead of modeling Q of t or phi of t or anything like that, or mu sub x of t, it models what's called the central death rate, m of x and t. Okay, so that central death rate, and basically it's the average rate of mortality, or the average Q between age X and X plus 1. Okay, and the model, it says, I'm going to write two expressions down. They're really all you need to know if you're handy with random variables. Is that we end up modeling the natural log of the central death rate. The natural log of m of xt is modeled as a constant, alpha, I guess I don't know why not a, that depends only on age, plus another constant depending on age, times a constant, well, actually random variable, depending on t. Okay, plus an error term, but we're going to ignore this guy. Okay, you can just think of it like this. Okay, there's a small random error term that we'll ignore. And unfortunately, k sub t is a stochastic process. It's a random walk with drift. So this is sort of this affects the rate of mortality improvement. Okay, and it depends on the previous k sub t. I'm just seeing how close I am to 6 minutes here. Oh, not bad. 7:08. So I'm going to get it done in 8 minutes. Okay, it's k sub t minus 1 plus a constant plus a random term. And the idea is, even though mortality declines with time, it doesn't decline in sort of a consistent fashion. There are new diseases, there are outbreaks of old diseases, there are wars that can bump up mortality now and then. So there's a random walk, and everywhere we see it, z is going to be a normal random variable, standard normal random variable with mean 0, standard deviation 1. Okay, and I needed to say one more thing. Oh, I think that's it. So that's all we need to know today. Okay, and I think we're ready to look at the first question. Before we look at the first question, I just want to remind you to look at this. Okay, that each year's mortality improvement is the old mortality from the year before times the improvement for the next year. All right, now, so if we were in class, I would say, any questions? And then we'd look at the question, but I'll just go ahead and look at the question, unless if I see something in the chat, I'll let you know. Oh, and I learned last class, I hope you found the recording, if you were looking for it, of the class. Last class, I found it was helpful to say, let me know when you have an answer, or you can type in GU for give up, okay, and that's fine too, and then I just know it's time to talk about it soon. Okay, so I'm going to start with the, let's not start with the sixth question. Let's start with the first question, and I'll give you a minute to think about it, and then I'll talk about it. So I'll try to give you about 3 minutes, or till I hear from you that you've given up or gotten an answer. So I'll give you some time to think about that. Okay, maybe I'll go ahead and talk about what I did here, and you can either find my mistake or we'll agree it's a different answer. So we're trying to find, we want the probability that the robot is still functioning at the end of 3 years. So we're looking for 3p0, which is p0 times p1 times p2. Now, p0 is today, so for p0, there's no mortality improvement. We haven't had any time yet. So p0 is just 1 minus q0, or q of x0. Let's say q of 0, 0, which is 0.6. Okay. And then for P2, it's gonna. I'm sorry. For P1, it's gonna be a little trickier to find Q of 1, It's what the mortality rate would be without a year of mortality improvement. So Q of 10 minus the rate of mortality improvement for a 1-year-old or a robot age 1 in 1 year. The rate of improvement at time t equal 1 for that. So that's 0.5 times, let's see, 1 minus 0.08 times 0.92. And 0.5 times 0.92, I guess, is 0.46. So Q of 1, that's a really bad Q there, is 0.46. And the notes and the SOA, they put tildes on Q sometimes. You can put them if you want, but this implies that P or P tilde, whichever it is, tilde just indicates with mortality improvement. That P1 is 1 minus 0.46 or 0.54. Okay, so we found P0, we found P1. P2 is a little more work. P2, well, we need Q. So Q of a 2-year-old robot, after which there have been 2 years of mortality improvement, is going to be the mortality rate for a 2-year-old robot with no mortality improvement times 2 years of mortality improvement. So times 1 minus phi of 2, 1 times 1 minus phi of 2, 2. Okay, so that's Q of 2, 0. So I got 0.6, that's this guy, times 1 minus that guy, times 1 minus that guy. So times 0.94 times 0.96. And if we multiply those together, I got 0.054. Whoops, wrong. I got 0.5414. Okay. So, and we can put a tilde on that if we want. So that means that P2, so P0, P1, P2, yeah. P2 is going to be 1 minus Q of 2, 2, I guess with a tilde. Okay, and that's 1 minus 0.5414, so let's see, that's 0.04586. Hopefully that's right. Okay. Okay, and that means the probability of surviving 3 years, 3p0, is going to be 0.6, the probability of surviving the first year, times the probability of surviving the second year, times the probability of surviving the third year. Well, this is like wrong. My decimal point's 1 too far to the left, I think. 0.4586. That looks a lot better. Let me erase that guy. There. That's what happens when you do things in your head. Okay, so 0.4586. And when I multiplied those together, I got 0.1486. And Justin made a comment for the last value. I see, right. So this is an important point, that you need to apply every year's mortality improvement. Improves by 6% the first year, 4% the second year. Okay, so I got C. All right. Any other thoughts or questions about number 1? So it's really, I don't know how you felt before, but this topic was not on the exam when I took it, but I would be hoping for this kind of question, because you can see they're really counting on folks being thrown off by the notation, and it's not super complicated. It's unlike the next, well, no, it's not the next one. The next one's not too bad either. It's the one after that that's a pain. The Lee Carter stuff's a bit of a pain. Okay, so I'll give you a chance to try to apply a cubic spline, and just remember, the idea is, so we know everything about mortality improvement before 2017, and we know everything about mortality improvement after 2027. But we don't know in between. So we're going to use a cubic spline of g of t, which is a cubic polynomial, to find a function that matches values and derivatives at these 2 points. And you have to sort of estimate the derivatives in the most obvious way. It's a little bit of hand waving in the question here, but it's still, I think it's okay. So I'll give you a minute to read this and try it. So all you're trying to do is find phi of year X. Which year is it? Oh, for 2022. You're just trying to find phi for 2022, in between 2017 and 2027. So it's been a good solid 5.5 minutes. Has anyone successfully found the value of D, the constant term? D is 0.037. Good, excellent. Okay, so we're making some progress anyway. Maybe I'll start through it. So we know we're going to be using a cubic spline. We know that g of t is at cubed plus bt squared plus ct plus d. And then we know once we find g of t, to estimate phi, we're basically going to want to find g of 5, and that's going to be our estimate of phi, because g is being used to estimate the improvement function between 2017 and 2027 in between these two values. Okay, so we're going to need g prime as well. G prime of t is equal to 3at squared plus 2bt plus c. With cubic splines, I always like to take a minute to write down the derivative because it makes me feel like, okay, there's something I got right with this question. But the first facts we have are we know that g of 0 corresponds to the year 2017, the last year for which we have data. And g of 0 is going to be 0.037. And if you evaluate this function at t equals 0, you just get d. So d is 0.037. And then g prime of 0, or the derivative in 2017, is approximately, delta y over delta x. It's approximately the slope, right? So it's approximately 0.037 minus 0.035 divided by the change in time, or divided by 1. Okay, so g prime of 0 is approximately 0.002, yeah, 0.002. And when we take the derivative, so 3a times 0 squared plus 2b times 0 plus, so this is just g, this is g prime of 0, plus c is equal to 0.002, so d is 0.037, and that just tells us that c is 0.002. Okay, so the good news is c and d are always very easy to find. Just look at the first point, set t equal to 0, look at the derivative and the value of the function, and you find c and d. The bad news is all the painful calculation begins now. Okay, so the other information that we have is that g of 5 is equal to the value of phi in 2027, 7.015. So 0.015 has to equal, for some reason I have 0. Oh, I'm looking at the derivative. So 0.015 is equal to a times 10 cubed. Okay, oops, that should be g of 10. I apologize. Is 0.015, which equals a times 10 cubed plus b times 10 squared. And luckily 10 is a nice round number. If you tried doing the one I put in the exercises, I used 15 instead of 10. So it was more of a pain, but still a great character building exercise. Okay, so plus c times 10 plus d. Okay, so 0.015. And the nice thing is we always get two linear equations plus two unknowns. 0.035 equals negative a plus b minus c plus 0.037. G of negative 1. You could, but we're supposed to be choosing a and b so that they're consistent with the other endpoint. I mean, specifically, the cubic spline is trying to match g of 0, g prime of 0, and then g and g prime at the other endpoint. Basically, what you would come up with is a good cubic spline for between 2016 and 2017. Great. Okay, so this is equal to 1000A plus 100B plus 10C. But 10C we already know is, let's see, C is 0.002, so that's plus 0.020 plus D plus 0.037. So if we do the math here, it implies 1000A plus 100B equals, this is 0.57 minus 0.015, so that's negative 0.042. Okay, let's keep that for a minute. That's our first linear equation. I feel like I need another color here. Okay, and then g prime of 10 is equal to, what are we given as g prime of 10? 0, that's kind of a lucky break. Okay, so 0 equals, let's see, 3a times 10 squared plus 2b times 10 plus c, which we know is, we found c just a minute ago, 0.002. that equals 0. So that tells us that, let's see, 300A plus 20B is equal to negative 0.002. So I'm going to write this as a system of equations with two unknowns. So we have 300A plus 20B equals negative 0.002, and 1000A plus 100B equals negative 0.042. Okay, and the way I do a system of two unknowns is I usually take one equation and subtract a multiple of another equation to try to eliminate one of the variables. The other alternative is to use substitution. You can do substitution, like solve the first equation for B and then plug into the second equation, but it's a real pain, okay? So what I'm going to do, and I'm just going to change the color of the marker to make it clear what I'm doing. I'm going to do the second row minus 5 times the first, okay? So if I do, and the reason for that is it's going to make the coefficients of B go away, okay? So if I do the second row minus 5 times the first, for A, if I switch back to blue here, for A, I'm going to have 1,000, so 1,000 minus 5 times 300. So that's going to be negative 500A. Plus 100B minus 5 times 20B is 0B, plus 0B, that's how I chose the 5, okay, equals negative 0.042 minus 5 times 0.002 is negative 0.042 plus 0.01, so that's negative 0.032. And now we're super happy because we have an equation with one unknown. And if we solve that, divide both sides by 500, by negative 500, sorry, we get that A equals, when I divided, I got that A equals, what did I get? Oh, a really messy number here, 0.00064. Which is actually not that hard to see. If you divide this guy by 1,000, you'll get 4 zeros and 3 2. It should be twice that because we divided by 500, which is half of 1,000, or 0.00064. Okay, so then we can use the first equation, actually we could use either, to solve for B. So plug and solve for B. Okay. I'm going to move things up again. If we plug and solve for B, we get that 300 times this number 0.00064 plus 20B is equal to negative 0.002. And these are really painful numbers. But if you do that, you get that B equals negative 0.00106. Okay, so now our spline is G of T equals that A, 0.00064 times T cubed minus, oops, this is worth erasing. It's worth erasing to get this right after all this work, I think. Okay. Minus 0.00106 T squared plus, is C positive or negative? So C was 0.002, so plus 0.002T, and D was 0.037, plus 0.037. All right, so the quantity we want to estimate phi, G is just for approximating phi between the two endpoints. G of 5, if we evaluate that guy by sticking in 5 for T, so there's 125 here, that's 5 cubed. There's 25 here and 5 there. If we evaluate G of 5, we get 0.0285. And that's our estimate for phi of X 2022, which was 5 years after 2017, where phi equals 0. So I'm going to go way back up and just check briefly which answer that was. That was 0.0285. Oh, wow. So we just hit D on the nose. So the answer is D. Okay, quite painful, right? I think on the SOA exam, it's more likely a question like this will be written answer, but it's a pain. Cubic splines, I don't know, they used to be important. I don't know, I guess they could still be a little important now. I consider that a hard question. It's one on the exam that I might save for last, but I definitely wouldn't skip because, I definitely know how to deal with a cubic. I mean, a polynomial is a nice thing to deal with. Okay, we deserve a short break after that, but no time for that. We've got an exam to pass, so let's see. Oh, and I heard today the exam is in April, so that's kind of exciting. I just added pressure to the conversation, I know, sorry. Okay, so take a breath. That's cubic splines, and the bad news is the easy part is now over. Okay, so the next question, I'm going to give a hint again. I'm going to give a hint up above, and then I'll move the question. But the hint is just that we're modeling the natural log of the central death rate of a person age X at time T. Okay, and after this, I'm probably just going to write the letter M instead of all that stuff. Okay, but that's a constant, alpha sub 60 in this case, plus beta sub 60, which depend only on age, times K sub 20. Okay, and that's true because we're interested in mortality in 2020. Okay, unfortunately, we're given K in 2018. Okay, so you have to deal with that using the fact that K, so I should just say K sub T, right? Yeah, that K sub T is equal to K for the year before, plus this constant drift factor, plus sigma sub K, the standard deviation of K as a random variable, times unit normal random variable Z. Okay, I'll give you a minute to work on that. A minute. I'll give you, what the heck, take 5. Take 5 to work on it. Okay, and then we'll talk. Okay, so to deal with this model that's up here in the green box, we have to deal with K sub 2020. Okay, and what we know is that it equals K sub 2019 plus this drift factor C plus sigma sub K, which is 0.9, but I'm just going to keep the variables for a minute, times a unit normal random variable. And really, the question, I mean, I'm going to go on record predicting that when this first appears on the exam, they'll give us K sub 2019 and not K sub 2018, because it just creates a lot of complication, and plenty of people are going to be thrown off these questions just by the notation. They're going to be ignoring it, and then the question would be much more manageable. But unfortunately, we have to iterate one more step here, because K sub 2019 is again K sub 2018, which we know, plus a constant, plus sigma sub K times another unit normal random variable. Those unit normal random variables are noise. They're not necessarily the same. So I'm going to give these two subscripts. Okay. So this means, oh, that says K sub 202. It should say 2020. So this means K sub 2020 is equal to K sub 2018, that factor in 2018, which we're given, plus 2 of these C's, because we substitute everything here in for K sub 2019, so plus 2C, plus sigma sub K, times the sum of 2 unit normal, presumably independent random variables. Okay, now when you add 2 unit normal random variables that are identically distributed but independent, the result is a normal random variable, still with mean 0, but with variance. You add the variances, so you get 2. I tend to write the standard deviation, not the variance, so I'd write square root of 2. That's the standard deviation, let's say, of Z plus Z, Z1 plus Z2. Okay, I hope this feels like progress. Okay, so this means that the stuff in green up there that we're trying to model, ln of m, okay, is equal to -4, that's alpha sub 60, plus beta 60 is 0.25, times all this stuff that is K sub 2020. K sub 2018, oh, plus there's this epsilon error term, but we ignore that. Okay, so K sub 2018 is given to us. That's -3. minus 2c's, the drift term is 0.05, so minus 0.1, that's 2 times negative 0.05 is negative 0.1. Okay, so this is 2c. Okay, plus sigma sub k times z1 plus z2. Okay, now we're getting somewhere. Okay, so look at what we have here. We have a normal random variable, mean 0, standard deviation, root 2. We're multiplying it by a constant. We know what happens to the mean and standard deviation in that situation. Everything else is just a constant being multiplied by constants or by this term. So this tells us that the natural log of the central death rate, and I'm going to move that 2c up so it's not in the way so much. Actually, I have an idea. Not exactly a stroke of genius, but I'm going to do it up here. That way it's not in the way. Okay, so this is, let's see, so negative 4 minus 0.75, that's the 0.25 times the negative 3, minus, minus 0.025 plus 0.25 times square root of 2. Well, let's just say times 0.25 times sigma sub k times n of 0 square root of 2. There, nice and easy. Okay, well, I wouldn't say easy. Hopefully relatively clear. Okay, so this implies, so this is just a constant plus a normally distributed random variable. So this equals, if I add those up, negative 4.775. Good. Okay, plus sigma sub k is actually given to us, 0.9. So if I multiply those two, I get, well, I'm just checking to see how I kept track of it so that my answers look consistent to me. Okay, good. 0.25. Well, let's just say n. N of, all right. I'm going to keep it as is, one more line. Okay, plus 0.25 times sigma sub k times n of 0 root 2. Okay, this is again a normal distribution. Here's the mean. So ln of m is equal to a normal distribution with mean negative 4.775 because that's negative 4.775 plus 0. This is 0.25. Okay, with standard deviation, the standard deviation here is root 2. We multiply that by 0.25 times sigma sub k. So that's 0.225 times square root of 2. Okay, whatever that is. Okay, and I'm gonna move this up a bit so I have some room to work. And I'm gonna change to the color green just to separate the work here. Just a lot better than red. Okay, so we're interested in m. M is e to the ln of m. So it's e to this normal distribution. Okay, so m is log normal. And there's this important fact that if the random variable y is defined as e to the random variable x, and this may hit you by surprise if you weren't expecting it. Okay, if you haven't read the notes or thought about this recently, but if y is e to the random variable x, it turns out that the expected value of y, you would kind of expect it to be e to the expected value of x, okay, or e to the mu sub x. Turns out not to be the case. It turns out the variance affects it. So e to the sigma squared sub x. This may come up in IFM. I'm not sure if you do like Black-Scholes there. It's just not occurring to me at the moment. But this affects the mean. Okay, so that turns out to be the expected value of y. So this should say then. Okay, so for us, that implies e of m, the thing we're looking for, the expected value of m, is equal to e to the expected value of x. Expected value of a normal distribution is just its mean, e to the negative 4.775, plus the standard deviation of that normal distribution, so that's 0.225 squared times square root of 2 squared, all divided by 2. Okay, and that turns out to be 0.0888. Okay, which is D. All right, 0.089. Okay, now that may make you want to leave for the night, okay? But please don't. The rest gets easier, okay? And the way the rest gets easier is it's all based on what I'm about to circle in red. I know I'm getting into the pen colors tonight. I hope that's tolerable. But the next 3 questions all use this fact. So the setup's exactly the same. The alpha sub 60, beta sub 60, and K sub 2018, C. They're all the same, and they all lead here. So keep in mind that the natural log of the central death rate is n of negative 4.775, comma, with standard deviation 0.225 times root 2. Okay, in fact, I'll write that on the next page for the next question at the top. Okay, so you can see on the next page, so I'm just going to write that down. ln of m, whoops. Wow, very first symbol's wrong. Okay, third time's the charm. Okay, it's Monday for me too. Okay, so ln, okay, of m is normally distributed with mean negative 4.775 and standard deviation, I think it was 0.225 times square root of 2. Okay, keep that in mind because the setup's exactly the same. And I want to be clear, on the exam, this here, instead of being K sub 2018, it will be K sub 2019, if that makes sense. It'll be 1 year earlier, not 2, because that introduced a lot of unnecessary complication that doesn't really test the question. Okay, so I'll give you a moment. You're calculating the standard deviation of M of 60 2020. Oh, and you're going to want to Google if y is e to the random variable x, you're going to want to Google the expression for the variance of y. Okay, I'll write it in a minute. Okay, so I'll give you a minute to work on that. And then if we're lucky, we'll be able to do one more before time's up. Oh, maybe I'll save you Googling instead. I'll tell you, it happens to be e of y, quantity squared, times e to the sigma sub x squared minus 1. Kind of makes sense. It's the second moment minus the square of the first moment. So we're helped out here by the fact that e of y, by exactly the previous question, S 4.3, e of y is just, what did we find there? 0.00888. Okay, and sigma sub x, we can read right off the distribution, also from 4.3 is 0.225 square root of 2. So that implies that the variance of y is equal to 0.00888 squared times e to the, let's see, I guess it should be 0.225 squared times 2 minus 1. And that turns out to be, this is going to be long, 0.00008400219. And the thing we want, the square root of that, turns out to be 0.00290. So it turns out to be A. So what can I say about this? So first, it's short and easy once they give us the distribution of ln of m. And this is not a crazy question to show up with that information given. But it would be hard to do, again, with all the other work that went into this. There was something else I wanted to say. Oh, this fact about log normal random variables, it seems important both to the author of the study note, Mary Hardy, and to whoever made the exam questions. Maybe it was her, I don't know. But it's probably worth keeping in mind. I can tell you, going into the exam, I would not remember this. I just would have no hope because my memory's not that good. But the one for the mean of y, I would remember. And I'd be ready to use it. I really think the most likely question on an exam is 4.3 with case of 2019 instead of case of 2018. We just have a couple more minutes, but it's worth noticing that S 4.5 has exactly the same setup. So I just want to warn you, ln of m, I mean, I'll let you work it without me, but ln of m, again, is normally distributed as a function, is a normal distribution with mean negative 4.75 and standard deviation 0.225 square root of 2, just from 4.3, the same thing. And you can work from there. And the important thing is the 95th percentile of m comes from the 95th percentile of this distribution. I wonder, maybe we should, it's 8:05. Why don't you give this question a try? Give this question a try for two minutes. I'll tell you what I think, and then we'll talk about what's happening in the last class on Wednesday. It's really not too bad. We really want to see this question with the stuff in green given to us. And I think it's just quite possible. And unlike with the mean, with percentiles and medians, things are very straightforward. Find the 95th percentile of ln of m, and then you find the 95th percentile of m. So since it's getting late, I'm going to go ahead and suggest the solution here. So the 95th percentile, or I know other folks say quantile. I'm not sure why. It sounds fancier, I guess. But the 95th quantile of ln of m, it's normally distributed. So we know to the 95th percentile that it's the mean. So let's just say mu sub x plus 1.645. I don't know if you remember that from your introductory statistics class, times sigma sub x. Okay, if I make a distribution, a normal distribution, and I have the mean here, and I go up 1.645 sigma, 5% of the distribution is going to be here. So this is equal to negative 4.775 plus 1.645 times 0.225 times square root of 2. And that number, the natural log of m, is going to be, I got negative 4.2516. And that implies m is equal to e to the negative 4.2516. Okay, so with mean, this doesn't work. With median and percentile, it works. With mean, we had those extra factors. And that turns out to be 0.01424. And that's the kind of number I kind of believe for a Q, or a central death rate, which is a lot like Q. So that suggests the answer is B. Okay. All right. So next week, so let me just, instead of solving the next question, which is the same idea, let's just say not next week. Sorry, on Wednesday. On Wednesday, we're going to talk about Markov chains and what appropriate questions on the SOA exam for Markov chains. And I think it's a great opportunity based on questions available to talk about written answer questions, okay? So we're going to use Markov chains to talk about what we should get into written answer questions, okay, when we write things out. Written answer questions, they tend to be, I mean, you want it to sound like you know what you're talking about, but in general, they're really graded on the inclusion of key terms. If you throw in the right words, even if you say things not quite right, you're going to get lots of points. Often they will start with a yes or no question, though, just to see, then they are distinguishing if it's more than using the correct terms, yes and no, you want to get the right one. But anyway, that's what we'll do next time. So I hope this evening was helpful. I think especially, so I think pure questions like number 4.1, I think you want to see those questions all day. I think they're easy as long as you know the process. Okay, cubic splines, we know what to do, but it's messy and arduous. I would save it for last, but I wouldn't leave it empty. And I really believe the questions they end up putting on there that have to do with the Lee-Carter model, if you're familiar with it, they're going to be not super overly complicated, because many people are just going to forgo studying for this material. And in fact, to be honest, I might have put myself in that group when I was taking the exam. But the question's not going to be too hard. There's only going to be one, but it's probably not going to involve this much calculation. Maybe with one step less, just with case of 2019. All right. I hope you have a great evening. Thanks for coming back tonight. I'll have notes for Markov chains posted by tomorrow around noon. And this, hopefully this lecture can be recorded by then as well for the folks that couldn't make it. So thanks. Good night.